Hello and welcome back to Watch This Space, our flagship series here at Haberdashers Adams Astronomy. I'm Mr. Nelms, continuing on our series on the life cycles of stars, and this week we're going to be looking at what happens next after the main sequence for stars that are sun-sized and smaller.
3, 2, 1.
Stars.
For stars that are significantly lighter than the Sun, anything from 0.08 solar masses up to potentially 0.8 solar masses, those sources vary on how light this is. Once they've completed the main sequence stage of their life and nuclear fusion in the core stops, the outwards nuclear pressure forces that were keeping it stable drop off, leading to a collapse of the star. The core at the centre of the star does not get hot enough to initiate fusion of heavier elements, with the star shrinking down to planet size as it becomes a white dwarf. Due to the collapse, the thermal energy within the star increases, heating up the surface of the star to become white hot, hence the name white dwarf. A white dwarf will remain in this phase for tens of billions of years, not undergoing any further nuclear fusion, but instead gradually cooling and transferring its heat back to the universe. Theoretically, a white dwarf will eventually cool so much that it will stop emitting light in the visible part of the spectrum, becoming a black dwarf. But the timescale for this to happen is longer than the age of the universe, meaning that this has not been observed in any cases. Unless a star is extremely light, when it finishes the main sequence, the collapsing core's temperature will skyrocket. This gets it hot enough to reignite the fusion process, but this time it will fuse helium inside the star to produce heavier elements. This causes a massive release of energy and a huge increase in the outwards forces in the star. As a result of this, the star will expand to a far greater size than it was during its main sequence. So, for example, when the Sun goes through this expansion, it will engulf Mercury, Venus, and potentially Earth as it swells to around 100 times its original radius. This expansion causes the heat energy to be more spread out throughout the star, and typically the surface will cool down to becoming red hot, hence the name red giant. However, for stars that were more massive on the main sequence, they might not be cool enough to become red, giving us supergiants that could be white hot, or in the most extreme cases, even blue hot. Once the helium has fused in the core, then depending on what size it is, after the core goes through further collapse, it can reignite and cause fusion of heavier elements. The very upper limit of this for a red giant is iron, although not all red giants will get this far. Beyond this, the fusion process no longer releases more energy than it requires to get started, so even the largest giant stars will not produce any elements beyond iron, at least not during the red giant phase. The painting that we can see here shows the relative size of a red giant, in this case Betelgeuse, against the Sun, which is the small yellow dot in the corner of the painting. After the fusion finally finishes within the core of a red giant, it will undergo one final collapse. But what happens next will depend on the size of the core and what temperature it gets to. For red giants that are under 8 solar masses, when they finish the final fusion in their cores, the core will collapse, becoming hotter and denser to form a white dwarf. But the red giant isn't stable before this, going through oscillations in size that can actually eject the outer shell and layers of the star up to distances of up to a couple of light years. As the white dwarf forms from the core collapse, it emits huge amounts of ultraviolet radiation due to the sudden increase in its temperature. This radiation is ionizing, and when it reaches the ejected outer layers, it causes them to glow. These planetary nebula are very short-lived on the timescale of a star's life cycle, existing for tens of thousands of years at most. The ejected material can eventually go on to form new stellar nebulae, giving a more complex cocktail of elements to collapse into the next generation of stars. The white dwarf at the centre remains there, cooling for tens of billions of years, unless it can gain enough mass to reach the Chandrasekhar limit, around 1.44 solar masses, at which point something spectacular would happen. And that concludes our second in our trilogy of videos on the life cycle of stars. Next week, we'll be looking at what happens for the heavier stars, going through supernovae, neutron stars, and looking into black holes. Not that we'll see much coming out of them. Until next time, please do consider subscribing to the channel if you haven't already to help us grow. We're nearly at that 500 subscriber mark, so it'd be nice to help us push over that line in the next week or so. Also, do give us a comment on anything you've enjoyed from this video or anything you'd like to know about stars and constellations in the rest of this series. And until next time, please continue to watch this space. Thank you.